Thanks for joining us today. This is the EDC5 Winter Webinar Series, webinar 9 of 10. Today is February 2nd, 2021, if you're joining us live, Groundhog Day. Today's topic is processing and analysis, making the most of your methods. So we have an exciting group of speakers today to provide presentations. And we have an opportunity, as today is going to be a extended session for question and answer period. So it'll be a great opportunity, I think, to share with you some of the exciting aspects of A-GaME technologies related to processing and analysis aspects. Earlier parts of the webinar series, we talked about individual techniques. And so today we're going to be exploring how and why and when we can make all of this happen for clients and customers and use in the A-GaME. Some of the things that we're talking about today are going to be related to using the A-GaME technologies in material property selection and design. Specifically, some of the conversations and presentations will relate to use of cone penetration testing data in numerical modeling, use of seismic CPT measurement while drilling as an opportunity to work with drilled shaft design, as well as visualizing and interpreting CPT and geophysical data, really with particular aspects of the processing and the analysis and how this relates to workflow for transportation projects. So presenters today, Augusto Lucarelli with Itasca, Jesse Rouser with LA DOTD, Peng with Ardaman and Associates, Christopher Krage, GEI Consultants, Mike Rogers at the University of Florida, and our special guest today for the panel discussion, Bill Owen with Caltrans, will be joining us. And with that, I'm going to turn the slide deck here over to Augusto to start us out. So I will stop my screen share here. Invite Augusto to share his screen. He's a principal engineer with Itasca Consulting here in Minneapolis, Minnesota. Worked on many numerical modeling projects for a variety of clients and geotechnical project types worldwide. So with that, Augusto, the screen is yours.
Thanks, Derrick, and thank you, everybody. Good afternoon. Thank you for attending this webinar. I hope that you will find it interesting. This presentation deals with the application of CPT tests for numerical modeling, in particular deformation analysis, calibrating the plastic hardening small strain constitutive model, which is widely used for static numerical analysis. Why CPTU, or possibly, preferably, seismic CPTU? Well, essentially because we can get many more data in a continuous way, and we can interpret many soil properties that are useful to profiling, consolidation, stiffness, in particular when you're doing a deformation analysis. The traditional way of determining the soil stiffness may be not representative of the volume that you are, let's say, engaging in the project. So, of course, you get much more information in essence. So whenever there is the chance, CPTU is a definitely interesting tool to implement. I don't want to rehash the debate between the SPT tribe and the CPT tribe, but really the SPT provides one number, and we are supposed to correlate all the properties that we see here on the right with one single number. That doesn't make me very comfortable. There is certain space for both, but in general, when we have soft soil or let's say loose sand, anytime, anywhere where the cone can actually penetrate a soil, there is no reason to do anything different. Now, we're going to talk about a few applications in a very superficial way. I'm sorry we don't have the time to go into any of the detail, but just to give you an overview of a few projects that I've been working recently. The first one is the Twin Port Interchange. Is a large project up north in Minnesota, Duluth. THC 169, again, is a project here in Minnesota. Both projects involve ground improvements. The 35W bridge, this is a project in which wick drains were implemented. Pond 1 backfilling, this is, we are going in Vietnam here. This is a typical case in which for a very soft soil, there were probably 50 boreals and 0 CPTs, and everybody was talking and fighting over the odometer modulus at layer number 9. And I said, why don't we do some CVTs and try to understand it better? And that's what happened. Wind turbine, again, this is a foundation analysis design in which ground improvement was debated, but then through the use of CPTs, we have been able to determine that ground improvement was not necessary for the performance. And then stockpile stage construction for stability analysis, again, using CPTs, in particular, the time-dependent dissipation test to determine the consolidation property of the soil. Okay, just a snapshot of the Duluth intersection. These just represent the 3D cross-section of the soil stratigraphy under an abutment. For this particular project, a large 3D model of the underground was built. You can see the sticks here that are representing boreal and CPTs, and all the layers were kind of reconstructed to determine not only the soil property, but also the bearing layers for the ground improvements. Now, what you usually do, besides recognizing and soil profiling, you try to determine, obviously, the properties. Here is an example of a shear wave velocity determination from a seismic cone. Using the red dots are the direct measurement of shear wave velocity, and the other lines and color represents traditional cone test without seismic. So as you can see, the Robertson 2009 correlation provides a reliable estimate of shear wave velocity, usually conservative, but especially for soft soil, it works okay. Here on the right, I'm not going to be able to talk about this. Essentially, this is the way to calibrate the plastic hardening soil model. You determine all the stiffnesses using the shear wave velocity and the Gmax, the Emax, and then the unloading, reloading in 50 NE odometer using this type of parameter. There is also there will be an extended presentation available on the website that will become available later on with further discussion about this. Other properties that are important for deformation analysis, obviously, is the stress history, the OCR, and the K-note that can be evaluated using CPTs. Strength, of course, there will be variability, so you have to get used to it. And this is an example of effective strength evaluation. You can estimate also permeability and coefficient of consolidation. So again, these are two parameters in which you have a lot of variability, but keep in mind that, at least for what I've seen from my experience, the permeability that you can estimate in the lab is 1 or 2 order of magnitude lower. And this is why when you're determining or evaluating settlement analysis, it takes forever. And then when you go on site and measure, and actually after 3 months, the consolidation process is finished. So the CPTs kind of provide something in between and more reliable in terms of, at least in my experience, in terms of evaluating the consolidation properties. And then you plug in all this property inside a model, and you get some insightful and interesting information in terms of deformation, soil structural interaction, and so on and so forth. This is the second project in which we had also the mass measurements for the shear wave velocity. But again, the strategy is the same. You start from the profiling. You have clearly a very weak soil here between 4 and let's say 10 meters, and you can determine pretty much all the property you need for your constitutive model from the shear wave velocity. And you can really be creative without getting carried away with trying to match as best as possible the soil profile without trying to overfit. This is probably one of the cases in which the overfitting was probably too much, but it worked very, very nicely at the end in terms of evaluating the displacement, horizontal and vertical. This is the 3D model for the embankment evaluation. Also, the interaction of the column, you see this blue line, you don't see it, but actually these are the column locations that are creating stress concentration. In particular, with this model, one of the issues was the shear strain concentration between the wall here and the regular section of the embankment. And so several measurements to counteract these potential risks were put in place. Let's move forward to another project. This is again a 3D representation of a 35W bridge extension. This is the new embankment that was built, and the soil was improved, quote unquote, using wick drain to accelerate the consolidation process. Here on the lower right, showing the measurement and the back analysis just using the CPT's data. Didn't play too much to try to calibrate or overfit anything. So this is with the CPT's profile, recognition of the soil, and then plugging especially the shear wave velocity to get the model, the formability and the over consolidation ratio for the stress history, and the permeability for the time scale effect. The volume treated with wick drains was determined and evaluated as an equivalent continuum permeability. So the wick drain evaluation was done on a separate, smaller model, and then an equivalent permeability was brought into the 3D larger model. This is one of the projects in Vietnam that I'm currently working in, which for a wind turbine generation facilities, we are essentially close to the ocean here, and some area has been backfilled, and the settlement have been measured in these 3 locations, in particular for this backfilling. And this is the site in which there were probably 50, even more, boreholes and not a single CPT. And then we started asking for CPT. You see the soil layering and the evaluation all the way down to essentially 60 meters until we have a competent dense sand. All this material is very compressible. And here at the top, we have a sandy, silty material. All the profiling that you can get from the CPT, you get a lot of information. And also this, the soil behavioral type, the normalized soil behavioral type is very interesting, especially when you're doing liquefaction analysis. It tells you what is the contractive or dilative behavior, something that you need to keep in mind for the evaluation of potential risk. This is not the case in this case, but there is a lot of application also in that area. A bunch of different properties that we can get and correlating with SPT, friction angle, and so on and so forth. Now let's move forward quickly to the measured. The preliminary evaluation that was done by the client in terms of settlement was very high, in the order of a few meters. In reality, when they measured, this is just 22 centimeters. So it's a quarter of a meter instead of a couple of meters of settlements. And that's why using lab data, especially if the lab is not really controlled, provide usually an overestimation of the settlements. And also the consolidation time would have been years, while you can see here that in a couple of months, the consolidation process is essentially done. This is the back analysis of the settlements carried out for the 2 locations. And really, in this case, I just plug in all the properties from the CPT using the soil behavioral type index, the modified, as a way to calibrate and determine all the other properties of the constitutive model. Wind turbine, again, site in which we didn't have any CPTs, and the concern was, do we need ground improvement to have a rotational stiffness compliant with the requirement for the turbine in this site? We asked for CPTs, and this is some of the profile that we got in terms of normal strengths. We have a silt, essentially dominantly silt at the top for 12 meters, and then a clay. Keep in mind that here for this site, we also had a shear wave velocity measurement from downhole, and here again a comparison between the Robertson correlation and the shear wave velocity measurement, which is pretty good. at least in this elevation. It tends to underestimate deeper location, but the reason is because this soil is age and present microstructure. In particular, something that we need to keep in mind is once we plot the shear wave velocity in the normal rigidity index here on the right, once you have this Kg, which is the ratio between J naught and the normalized cone resistance, if we are in this range above 330, it means that the soil presents significant microstructure, aging and cementation, which is good, obviously for the site response, but it's difficult to capture by the CPT. So that's why, in general, for this type of soil, the CPTs provide, let's say, lower evaluation, lower estimate. Now, the shear wave velocity design for this wind turbine was selected in a very conservative way, using not even the cross hole, but rely on the average of the CPT's estimation. This is the foundation geometry. And everybody's concern for this large footing is the bearing capacity. While it is not a problem of bearing capacity, it is a problem of rotational stiffness to comply with the requirement, and essentially frequency to comply with the wind turbine demand. You see that here in this case, what I did is a rotational load test, so incrementing the load all the way up to failure to see which one is going to fail first, is the soil or the structure. And what happened generally in this type of foundation is that the concrete would fail first before reaching any type of geotechnical capacity. You see the cracking formation in the concrete, you see the steel engaging all the full strength and actually yielding. And to show what's happening in progress, you see the progression of the failure on the concrete side. So this is something that is interesting also for the numerical side, that is not only related to the geotechnical aspect, but sometimes is the combination of structural and geotechnical that needs to go together to try to understand better and optimize where the resources should go. Is it better to invest in a stronger concrete or to try to do ground improvement? It wouldn't make any difference here to ground improve other than improving maybe some concrete detail. Now, finally, I think this is the last one. This is a big stockpile for a mining facility that was supposed to be built on top of a clay. This green, dark green is a clay that shows from the CPTs these two different profiling in terms of CH. You see the one red line and a blue line. So one is faster, one is slower. And what would happen if we apply the construction stages provided by the mine on top of this clay? At some point, one of the two layout in particular for the blue line, we have a geotechnical failure, because the loading rate that they were thinking was too fast. And you see all this spike in the pore pressure generation. It means that the model becomes unstable, and you clearly see the formation of a classical circular failure envelope. All these analyses are done in drain condition. There is no undrained shear strength in any way, shape, or form. It's the interaction between the skeleton and the fluid that determine through the volumetric property of the water, the pore pressure generation during construction. This one is the reddish. Everything was fine with settlement that are completely tolerable and the pore pressure that was able to dissipate. So the advantage of doing in situ dissipation test for this particular soil when construction stage is important, I'm thinking about dam, for example, is quite significant. Some other data about the analysis, but I believe this is the last one. Okay, thank you for your attention, and I will get any question after the panel.
Okay, thanks, Augusto. I think that provided a lot of insight to the various ways that cone data can be processed for use in numerical analysis. So We're going to have a tag team presentation. So our next speakers, Jesse Rouser is an assistant geotechnical administrator with the Louisiana Department of Transportation and Development. He's worked for the department about 10 years and private industry for 8 years prior to that. And his interests include deep foundation design, testing, and data management. He'll be joined by Dr. Xin Peng, geotechnical engineer at Ardaman and Associates, also in Louisiana. He specializes in using high-level programming languages to develop web-based geotechnical and geoenvironmental database management systems for advanced data visualization and analysis. So take it away.
Okay, Derrick, am I sharing the correct screen?
You are. You're good to go.
All right, thank you. All right, thanks everybody. I'm going to go kind of quick here and try to let Xin get to some of the cool stuff. But what we're going to present to you today is a project that we've been working on jointly for the last year or so. And it's still a work in progress. It will probably remain a work in progress for a long time. But hopefully we can demonstrate some of the stuff that you can do if you just kind of think outside the box a little bit. Xin, like Derrick said, works for Ardaman and Associates. They're one of our consultants that we have on retainer. And a while back, he demonstrated a project he was working on to kind of take all the geotech data from one of their larger LADOTD projects and plot the data in a web browser. And so he already had, you know, the core of this thing going, and he had a laundry list of features that he wanted to implement. And I also had some wish list items from a kind of a data management standpoint. And so we worked together to try to incorporate his web-based system into kind of our overall future data management plans at LADOTD. And then so before I let him show off some of the features of the web-based visualization tool, I want to talk a little bit about some of our big picture needs as a state DOT. And I'm probably going to preach to the choir here, but with some of these needs. But I just want to illustrate kind of how we end up with some of these cool tools like Xin's going to present. And I want to show these things kind of in terms of where we used to be and where we would like to be. But keep in mind, it's a sliding scale, and in some of these cases, we're definitely in the middle. And I don't want to marginalize the efforts or any of the work that anybody's done on our behalf to try to just get to the middle, because a lot of it's been a ton of work on a lot of people's parts in those cases. But we still have things that we'd like to do, obviously. So kind of where we started with our borehole data was that our drill crew, they would just log the soil borings by hand with the sample still in the Shelby tubes. And the engineer wouldn't really see the samples or assign any testing. And eventually we'd receive boring logs from the geotech lab, and they're located in a different building. So there's kind of a disconnect there. And then the lab would also retype all the boring and sample information. Each project would be saved in a separate GENT file. And our consultants kind of do the same thing. They'll submit separate GENT files to us, and ultimately it keeps it, or makes it hard to keep track of our geotech data from a regional or a geographical level. We're looking at everything on a project by project basis. And you know, finally, the kind of the main deliverable from our consultants is that they submit stamped paper boring logs to go into the plans. And so where we've kind of started to change our workflow is that the engineer responsible for the project is going to extrude the samples when they come in, and he logs those samples on a tablet. And pretty much what this does is it kind of begins a digital chain of custody. And so that hopefully in the future, project numbers, boring names, sample IDs, et cetera, don't all have to be re-entered again. And so we'd eventually like for all our geotech data to be transmitted using a standardized interchange format without a lot of data re-entry. And Jen's going to touch on that later when he talks about digs. And you know, ultimately we want to have all of our borehole data in one central database and be able to focus on the data as the final deliverable and not paper logs as the final deliverable. So with our cone data, we would generally receive individual data files from the drill crew, and then the engineer would just kind of process the data and plot the sounding logs. And you know, usually when you want to use it, you take that CPT data and kind of indirectly correlate properties for foundation design. So we do some direct design methods now, but you know, kind of where we started was indirectly using CPT data. But where we'd really like to go in the future, and some of this we're doing now, is to get our CPT data directly into that same database that we're talking about. Once it's in there, we can develop specialized tools to visualize the boring and CPT data together, and then do automatic functions like automatic stratification, correlations, calibrations of things like NK factors. And the reason I've got this highlighted in the presentation right now is because, you know, some of what Jen's going to present, you know, this kind of highlights that. Beyond that, I think we can eventually develop tools that take these data sets and do automatic calibration of resistance factors, direct design methods, and things like that. And so with site characterization, this is kind of one of my biggest pet peeves where we are with this. You know, I feel like a lot of times I go to, you know, you'll go to TRB and go to these conferences and hear all this really great high-tech stuff. And then you think, well, we still can't hardly characterize the site correctly. So, you know, I think a lot of what we do needs to really focus on site characterization. So normally for us, when a new project comes in, an engineer tries to find historical data that can be like looking for a needle in a haystack, unless you're rebuilding an existing bridge where you've got as-built. And then when the boring logs come in, the engineers manually type all the data into a spreadsheet, manipulate the data manually in the spreadsheet, plot the site conditions. And the reason I've got engineers highlighted 3 times here is I think that these 3 bullet points are really the source of the biggest waste of engineering time on most typical projects that we work on. And so being that we're kind of wasting time doing some of that stuff, where we'd really like to be is have all this geotech data geolocated in a database with tools to get it out quickly so that the engineer spends more time understanding the site and selecting good design profiles. And so ideally, if we know where the project is, we should be able to plot all the known geotechnical data and get a rough idea of the stratification and the variability of that data within just a few minutes. And that's completely doable, I believe. And Peng's going to demonstrate where he's going in that, you know, in terms of that. In terms of our reliability-based design, you know, I think most of us, at least in state DOTs, are probably in the same boat in that well, all of us really are, we kind of select our design profiles or site conditions based on our own engineering judgment. And then we design foundations using recommended resistance factors. And luckily at LADOTD, we're fortunate enough to have a really good research group at LTRC, and they've done some regional calibrations for us, but it's still a lot of work to gather more data and to go back and revisit these calibrations periodically. So as I mentioned before, you know, from a reliability-based standpoint, we'd like to be able to stratify our soils and compute variability automatically. And that could lead us to some site-specific resistance factors, very much along the lines of what's been researched at MoDOT. And eventually with large enough data sets that include test piles and test shafts, we might be able to look into some automatic calibration of design methods and resistance factors. From a construction testing and construction support standpoint, you know, speaking of test foundations, we do keep a test pile database. It doesn't really have any real data interchange functionality with any of our other geotechnical data. But what we'd really like is to go to a point where we've got test piles sitting in that same database alongside our boreholes and CPTs. And that way we can start comparing test results with geotechnical data and our design methods. And then also kind of with respect to construction support, as geotechs, we do make a lot of field visits for foundation testing, just general troubleshooting. And, you know, a lot of times we'll have to grab a set of plans and a set of boring logs to try to help us make decisions in the field. And our construction folks, they have started using tablets to document construction, but in the geotech group, we don't have access to that yet. But, you know, looking forward, you know, kind of one of the things I've been thinking about is if the geotechnical engineer had access to a tablet and all this soil data in the field and ways to manipulate, you know, view it remotely, manipulate it, we could make a lot better decisions in the field and, you know, hopefully save time and money, you know, from a contracting standpoint. So just to kind of summarize, you know, we want to standardize our data entry and interchange, as well as treat our data as the deliverable, not the paper boring logs. We want to cut down on data entry and manipulation and reuse as much of our data as possible. We spend roughly $10,000 to $15,000 per deep boring, including the testing and boring logs, and 5 to 10 times that much for a static load test. So if we're not reusing that data for new projects or at least research, to me, that's a huge waste of money. And so we want to get our geotech data all in the same place, or at least kind of have our databases talking to one another. And then ultimately, if we have good quality data and we can develop ways to use it to make better engineering decisions without clutter, you know, from either the office, from meetings, or from the field, anywhere that, you know, we really need to make quick, informed decisions. And so before Shin takes over and kind of presents his work, it kind of brings up a question, you know, what if we could plot our data from any project in any number of ways from any device with a web browser? You know, how would that change the way we work? And that's pretty much all I've got. And I want to turn it over to Zen Peng at this point.
So good afternoon, everyone. So can you see my screen?
Yep, we can. You're good to go.
Thank you. So this is Peng from Ardaman Associates. So thanks, Jesse, to introduce the current status and the long-term goals of the overall geotechnic data measurement implementation at Louisiana DOTD. So we are currently collaborating with each other to achieve each of those goals step by step. So in my today's presentation, I will briefly introduce some of our preliminary work of developing a Geotechnic web-based system. So parts of its feature I'm going to introduce today is about how to load and stack DIGS files and interact, visualize, and interpret soil boring data simply using a web browser. In addition to that, I will also briefly introduce some additional features within the web system with CPT and geophysical data visualization, as well as some additional reliability design consideration within this web tool. So as we know, so we're currently moving into the age of big data. So this figure shows the amount of data we created, captured and replicated across the world each year from 2010 to 2025. So as we can see here, the data we are generating have been increasing exponentially, and we are expecting to generate 175 zettabyte data in the year of 2025. And you may be wondering what is 1 zettabyte? So 1 zettabyte is equal to 1 billion terabytes. So what behind the data explosion? So as described by a VP at Google, so there has never in human history been such an information explosion. Everyone could attribute this to the rise of smartphones, sensors, and connected vehicles and appliances, among other digital artifacts. Much of what we touch and work with now automatically generates data, but the real reason why we are seeing this increase is the growing utility of data analytics and automatic responses to analytic decisions. So as more advanced geotechnical methods have been implemented, just like all these A-GaME methods, we will need to transfer, visualize, and interpret those data in some efficient ways. So as Jesse previously mentioned, so one of our goals is to centralize all different types of data into a database and then let them effectively and efficiently talk to each other to facilitate the overall geotechnical design workflow. So as we're dealing with more and more geotechnical data, it would be extremely important for us to visualize and interpret data properly and efficiently. So by doing this, we could potentially reduce the design uncertainties, increase the design efficiency, and improve the design quality. So one of the very useful geotechnical tools is called DIGS. So probably some of you have already heard about it for a long time. So basically it's an open source standardized data formats for digital transfer of geotechnical and geoenvironmental data. And there are many features of using DIGS. So first is open source. So which means it's free to use and it's highly customizable with schemas to meet different data transfer needs. Also, it's standardized data transfer format, which means it will facilitate the overall data management workflow, and you can easily transfer and share data with others. And you can also stack, visualize, and interpret different types of data directly using DIGS files. So speaking of the Geotechnic web-based system we have been developing, so here are some of its major features. So as Jesse previously mentioned, so we can use it from any device simply with a web browser and without any software installed locally. And then we can import and stack data directly from DIGS files for any projects. Besides of that, we can also directly stream data from cloud database. So once we have all the data loaded from DIGS, either from DIGS files or cloud database, we can not only efficiently combine, visualize different types of data, but also can perform some advanced statistical data analysis as well as engineering analysis. So in the next few slides, I will briefly introduce some of these features with some examples. So here is a screenshot of the DIGS version of this web-based system. So we can load one or more DIGS files using the uploading tools here. And here is a simple example of the DIGS file ready for loading into the system. So we're currently helping Louisiana DOT generate DIGS files directly using GaME files. So here is a short video to demonstrate the DIGS loading process in this web system. So once, as you can see here, so once the DIGS file is loaded, so you will see some the borehole locations updated in the map, and you can always customize the symbols and labels in the map as we need it. And we can also stack DIGS files from multiple projects. So here shows an example of loading and stacking with DIGS files from 3 different projects in Louisiana. So this can be very useful when we need to reuse historic data and compare them with new data for a given project site, or for multiple project sites but with very similar geotechnic subsurface conditions. And once we have some soil borings selected in the map, we will see some data profiles automatically generated based on the map selections. So this is an example demonstrating how we can stack and visualize data from multiple projects. Here we have about 190 soil borings from 3 different projects selected, and data points from more than 4,600 soil borings are displayed in these data profiles. And with a few simple clicks within this tool, we can instantly have the data profiles from any combination of soil borings from one or multiple projects. Think about how long it will typically take if you would like to export data from 4,600 soil samples from multiple GaME files and then plot them in an Excel spreadsheet. So by the way, so this tool also provides an efficient way to identify some outlier points, as you may notice. So here we have total unit weight points greater than 200 PCF. So it's definitely an outlier. So here we can easily find out which projects and which soil borings it belongs to. And then we can either remove or correct it before performing any data analysis. So once we have a preliminary design which identified by combining some soil borings and also remove some outlier points, we can interactively visualize some statistic features in each auto-stratified data profile. So here we have a yellow band, which is the moving average minus and plus one moving standard deviation. And we also have a moving average line in red. And we also have the auto-generated auto-stratified soil layers, stratified layers based on the local peaks of the moving coefficient of variation. Also, the coefficient of variation within each stratified layers is also automatically calculated and displayed in red on the right-hand side of each figure. And based on the Federal Highways GEC5 geotechnical site characterization, the coefficient of variation within each stratified layer should be less than 0.3 for a reliable design. So To achieve such goal, we can manually further remove some outlier points based on our engineering judgments in any of these data plots, or we can adjust the data window size to re-stratify each data profiles. So after we finalize the soil stratification, so we could develop some preliminary design soil parameters for the design reach. So in this example, with the data points removed by click the interactive legend on top of each data plot, we can clearly see 3 design lines which are generated in the total in the soil unit weight, shear strength, and N60 plots. So here we have red mean lines, and also we have low bound green lines, which are 0.25 quantile of the data points within each stratified layer. We also have 0.75, the upper bound blue lines, which are 0.75 quantile of all the data points within each stratified layers in each data profile. And also we could, if we would like to manually adjust these quantile values for the boundary design lines based on our local experience, we could simply adjust the range sliders on each of the top plots. Then the boundary design lines can be shifted automatically. In addition, if we don't like some of the auto-generated soil layers and soil parameters, here we have a design table, so we can still use our local experience to further refine them by manually adding or removing soil layers, updating layer elevation of the layer boundaries. And we can also manually change soil types and corresponding soil parameters in each stratified layer based on our own engineering judgments. So after we finalize this design table, we could export this table to Excel spreadsheet for further analysis if we need. Here we can also generate some interactive fence plots to help us further refine design reaches, stratify composite soil layers, and develop soil parameters. And we can also interactively view the detailed soil description of individual soil layer within this within each soil column, as we can see here. So if you're interested in seeing the complete demonstration videos of this version of the Geotechnic web-based system, please feel free to visit GISDIC's website. So currently we are actually implementing several other features within this web system. So in this example, we have been managing data from more than 300 CPT soundings and about 30 2D and 3D electrical resistivity surveys. Here we have, in this map, we have 1 ER survey line selected, which is highlighted in yellow. And we also have 4 nearby CPTs selected in the map. By simply click a button in this web tool, we could instantly get an interactive cross-section graph with all the data combined. And as we can see here, so the CPT data and the ER contour are quite consistent. Typically, the cohesionless soils have higher electrical resistivity than the cohesive soils. As we can see here, so the cohesionless soils, which are in gold, yellow, and red in the CPT columns, as you can see here, are pretty consistent with the boundaries of the comparative high ER values. So think about how typically you combine these 2 types of data in a cross-section graph in your design workflow. In this web system, you can visualize and compare any ER survey lines with nearby CPTs within a minute. In this tool, we can also interactively visualize and manipulate 3D volume plots for 3D ER surveys. Here we have 2 parallels ER surveys selected in the map. And this is the interactive 3D plots for the combination of these 2 surveys within the web tool. So since we are able to develop design parameters within the web systems, we're also trying to implement some features related to engineering analysis. So in this case, we have developed, as I previously discussed, we have developed the low bound, mean, and upper bound design parameters for power analysis. and we can select any of these design parameter data sets for design calculation. So in this case, we used mean values. So after specifying the power properties, some power properties, we can simply click the button to run some power resistance analysis within a web browser. So here we can review the calculation results of the total nominal resistance and skin friction and bearing, and we can export them to Excel spreadsheet if we would like to do. Also, we can interact review the resistance profile within this web tool. So as Jesse mentioned earlier, so engineers eventually will design foundations using site-specific or even layer-specific resistance factors based on data variability. So Missouri DOT did some great studies to identify the relationships between the resistance factors of end bearing and the coefficient of variation of ungrained shear strengths of, for sharp tip resistance calculation in clay. So in our web system, we can always automatically get the coefficient of variation of ungrained shear strengths or any other type of soil parameters within each stratified soil layer. So it should be straightforward to apply the COV dependent resistance factors in the deep foundation design in our web system. So in summary, DIGS is a standardized data transfer format for geotechnical and geoenvironmental data, which can be efficiently used in a web system for interactive data visualization and interpretation. And the web-based system, database system allows engineers efficiently identify design features, stratify soil layers, and develop soil parameters with incorporation of variability and uncertainty considerations. So in addition, local engineering experience can also be easily incorporated in this process. So advanced data visualization and interpretation features for other advanced geotechnical site characterization methods, such as CPTs and electrical resistivity imaging and etc., can also be incorporated into this web system. Foundation design using site-specific or layer-specific resistance factors based on data variability will also be incorporated in the later versions of this geotechnic web-based system. So that's it. Thank you so much for your time. And if you have any questions, please feel free to contact us. So let me stop sharing my screen and give it over to Derrick.
Okay. All right. Well, thank you to both Jesse and Jin for the presentation today. You know, I think that that presentation speaks to the real power of processing the information and actually using a lot of the robustness of the data sets, what we can do with all of the mostly digitally delivered information. So thank you. Our next presenter today is going to be Dr. Christopher Krage, project engineer in GEI's Sacramento office, specializing in geotechnical engineering. His professional experience includes site exploration, characterization, and performing static and seismic stability analyses for a variety of projects and team environments. He's also served as a lecturer at Sacramento State University, teaching a course on geotechnical earthquake engineering.
Thank you, Derrick, for the invitation, and I'm happy to be here and to be able to present in support of this A-GaME webinar series. And so the topic that I'm presenting on today is mostly actually a project example where we use this kind of integrated approach to site characterization using several different tools, relying on the Seismic Cpt, and how we used that to support our feasibility and design level analyses for this project. Now, I know that this is a FHWA seminar series. This project example that I'm presenting is a pipeline project, but it was a fairly large, extensive reaching pipeline, and so has some similarities with regard to some more DOT type studies. So I hope you find it interesting. Quick outline just for what we're going to go through. I'll spend just a second on the overview for the approach, the integrated approach to kind of frame this effort. look at a few of the different tools that we are using in support of this evaluation, and then we'll jump into the pipeline project example. Some key highlights we'll get into are, again, the Seismic Cpt, the use of the Seismic Cpt, and how we could rely on that for performing site-specific site response analyses, both in 1D and 2D, as well as liquefaction triggering analyses. And then just a quick conclusion to wrap it up. So an integrated framework is helpful to consider, when you're looking at your project, going out and framing your site investigation efforts within this context. This is an example context, one that was written up by Professor Jason DeYoung at University of California, Davis. And so that reference is there for you as well. But essentially, there's some key components here, and it's going to be your desktop study, which should be completed before going out, even kind of when in support of the design of the exploration program, where we're going to gather all the available information that we can on our site and on our region, looking at historical information, aerial imagery, and kind of coming up with what is our hypothesis? What do we expect to encounter? Because that will really help us with regard to selecting the appropriate tools for our site investigations. Then we'll go out and do our SI work, and then we'll come back and start processing through that data. And that brings it into this synthesis or site idealization phase. And of course, this is a feedback loop. So sometimes this is happening on a daily basis, where you're going out, you're collecting CPT data, you're interpreting that data in the evening, and you're using that, or the next day, and you're using that to adjust or modify your exploration program on the fly. Or it could be in support of a phased effort, where CPTs or some other high production rate technique can be used in advance of some more targeted or specific lab test or vein shear test operations, as was performed in this study. And then, of course, this all affects the analysis and design. And so if you have just a limited data set, there's going to be some larger uncertainty. And so that will come forth with regard to the analysis and design phase. And that may necessitate returning to the field and doing some more explorations and repeating this process. And again, some of the key concerns that need to be addressed are what's the uncertainty that we have with regard to our geotechnical property characterization in terms of the actual numbers used, but then also what is the potential impact of spatial variability on the project? Do we expect to see multiple different subsurface stratigraphic zones and units that are encountered for this design? And do we need to adjust our design or adjust our analysis to consider that variability, or do we need to go in and collect more data to really hone in on where those transition zones could occur? So some of the key tools that were used in this study where we did some like I said, we did CPT testing with seismic readings. We also did some traditional mud rotary borings and SPTs with collection of tube samples for high quality laboratory strength testing, as well as we actually did some vein shear tests for some additional in situ shear strength data collection. And so we'll show you a little bit of how those all play together on this project. So the example project is a pipeline project, and our purpose in it was to perform a geotechnical exploration and analysis to support this feasibility level study of this pipeline. And the pipeline included several different components, including a horizontal directionally drilled pipeline beneath the harbor in Oakland, California. So we had to collect subsurface data along with proposed alignment. We had to assess various seismic hazards and investigate potential need for or sizing of ground improvement measures to mitigate hazards. And then come up with the design level recommendations and actually ended up doing some design level analyses for this project. So some of the key features, just an overview, over 13,000 feet of pipeline, including about a 2,900 foot HDD pipeline through the underneath the harbor. And then both the approach and the cut and cover pipelines are 24-inch diameter. However, they're constructed of different material, which affects the design, you know, and informs the design as well. So the HDD pipeline is rather flexible, whereas the approach pipelines were more of a traditional steel pipeline, and so those were more rigid and less flexible. And so that comes into play with the potential settlement and deformation analysis that was performed for this project. So now I'll just give you a quick overview of the site. So this, again, project is located in Oakland, California. This is shown here that basically this additional pipeline here is being proposed to provide a lifeline service to Alameda Island, which is isolated from other potential water sources. So in the event of some collapse of the infrastructure system due to an earthquake or some other natural disaster, then they would have a lifeline pipeline. So this is one of several that is being proposed to be constructed to support Alameda Island here. And so, but if we just zoom out a minute here, for those that are unfamiliar with Bay Area geology and geomorphology, what we're dealing with is actually a rather complex geological system, in that we have alluvial fan type deposits, as well as a bay. So we've got western and marine type sediments as well. And then we have a harbor. And so there's an ever-evolving shoreline. So there's just a lot of variability to consider, and that does impact the techniques and that we can use for collecting our geotechnical data, as well as understanding the variability that would be expected at this site. So this is a summary, plan view summary of the design layout, with several different reaches kind of called out. The blue reach towards the right of your screen is the cut and cover alignment on the Oakland side. The yellow reach in the middle is the flexible HDD pipeline that is going to go under the harbor there. And then the purple line is the cut and cover pipeline on the Alameda segment of the pipeline here. And so the exploration program was rather extensive. It consisted of 8 onshore and 4 offshore borings, 22 CPTs, 8 of which with seismic readings, a couple of vein shear tests, as well as some marine geophysics and environmental screening work. So going back to the integrated framework, the first thing that we do is perform a desktop study. And so that's a collection of not just historical aerial imagery, but also historical geotechnical data. And in this more relatively dense urban environment, there was quite a bit of historical data to cull through as well. And so this is just an example showing here that the change, the transition in some of the shoreline over the years. And so things like old piling and old decking from some facility here that was going to be a challenge, or at least required kind of the setting back of this pipeline, this HDD section of the pipeline, so to avoid some of those timber piles. Another example here is some historical evaluations and published data sets on material type. And so in this case, we've got some rather thick deposits of what's known as locally as young bay mud, which is a silty clay with some plasticity and is very compressible. And so this tells us where do we expect to see that data, where might we want to concentrate some greater characterization efforts for coming up with our design properties, our analysis properties for the bay mud in this project. Another example is some published liquefaction susceptibility maps. So this is from the USGS. And so the red image, the red colors in there are showing areas that have high susceptibility to liquefaction triggering. And that would be, you know, these are nearshore soils. So some of them are artificial. So thinking loose and low density layers that would be saturated and susceptible. Whereas as you move further away from the shoreline, you picking up some more natural and aged deposits. So again, now we're going to go to the field. And so, you know, we've got several different tools that were used on this project, including Seismic Cpt, as shown on the left here. In the middle is actually an overwater barge boring. So this is a traditional mud rotary drill rig on a barge that was used to collect information within the harbor. To the right here is vein shear testing. So these are a few different veins, vein sizes, and the size of the vein will depend on what the anticipated strength of the material interest would be. Something that is softer, you can use a larger vein on, and something that is stiffer, you need to use a smaller vein on to be able to rotate it and torque it appropriately. And the bottom image is the contractor performing a vein shear testing interval. And then these other two images here are actually the photos of the marine survey to come up with some of the bathymetry between the two land locations. So the next several slides will focus in on our approach to site idealization. And so the first thing that we did was come up with, again, what are the different reaches and stratigraphic interpretations we have along this pipeline alignment. And this is one example of what that cross-section could look like. And so here we're actually projecting our CPT data with our interpreted soil behavior types shown in the different colors as evidenced with this legend down here below. And so we can project those CPT interpretations both with soil behavior type as well as our tip resistance profiles and sleeve friction profiles. And that really aids in the interpretation of the subsurface stratigraphy. And this example here is actually showing the transition into the harbor as we start to see the thickness of the bay mud deposit, which is the clay material, really start to pick up as we move in towards the harbor. As well, you can see some of these denser sand layers, again, peter out as we approach that harbor region. Another thing that we did for this project for supporting the site idealization phase was, again, we collected several different CPT, seismic CPT measurements. And we were able to, at least the process we used here was breaking down from those cross sections and from our interpretation of each CPT, can we break down our readings into material classifications. And so that's just showing in a breakdown into just a summary of the shear wave velocity readings as a function of the material unit. And then we repeated that for all of the available CPTs, as well as some historical downhole suspension logging data sources to come up with trends. And so this is an example, or this is a summary plot. These are all to the same y-axis scale, but you can see here the differences between in both the young bay mud shear wave velocity data set, which is rather tight along this best fit line here. And then when we're looking at something that's a more of a denser underlying over consolidated material, there's a lot more variability in the older alluvium. And then there's some other sandy deposits that we can select representative profiles for our design and analysis. And this is important when we're going to do this type of work, this type of seismic evaluations, because we do need to infill some of the gaps that we have, particularly with the horizontal directionally drilled pipeline, we weren't able to collect data at every, as frequently as we would like along the section line. And so we need to rely on our characterization information where we have it, and be able to apply some confidence to that data set for our idealization of the site. And then this is another example of how we might, synthesize the data that we do have. So, these are great ways. We call these monster plots, but this is a great way to summarize all the various data sources that you have for a given location, to come up with what are our representative properties for analysis and design. And so you can see here on the left side is a stratigraphic interpretation. I've extended the red lines across the charts here for reference. But you can see that as we pick up both in terms of blow count data and CPT data, we can pick up a transition into what's more of a normally consolidated or near normally consolidated clay, and then picking up into something more over consolidated in terms of both tip resistance and blow count data. And then that's also supported by our favorite index tests as well. So PIs, Atterberg limits, and water content readings help kind of confirm some of that interpretation. In this case, the undrained shear strength of this bay mud material is really important to understand. And so coming up with the recommended over-consolidation ratio profile it is key. And the CPT was very useful in filling in the data gaps, given the limited sampling that was performed for this project. And then undrained strength characterization. There's lots of different data sources for coming up with what is our undrained strength. You've got your more index style evaluations, your pocket pens and your Torvane tests. And then we've got our CPTs, we've got our lab triaxial tests and our vein shear test data. This is an example here of the vein shear test data. And so this is plotted in a normalized undrained strength versus vertical effective stress versus OCR configuration, is typical to a stress normalized framework. And so we can see here, based on the data set and then selection of what we think the representative fit of that data would be, both based off the data that we collected as well as available information from local knowledge. And then, of course, we've got trained strengths from our triaxial data to support our interpretation as well. Next would be to take that idealized data, and now we're going to bring it into a framework where we can evaluate and analyze representative profiles. And so this is just an example here of a 1D site response analysis that is built and constructed primarily off of our CPT data. And so we can see here, again, our interpreted stratigraphy. We can look at the various sources of CPT data that are used to support this, within this given reach, and then our interpreted and regressed via shear wave velocity profiles that are used in our site response analysis. And then, we can look at performing our analysis. We can key in on what are some of the key observations that we see here in terms of things that are of interest with site response. Would be things like what are the peak shear strains. And so we can see really highly nonlinear, these are large ground motions that are being used to design this project. And so that's pushing the soft bay mud into the nonlinear region. And so then that has an effect on site response. So that can de-amplify and reduce some of the seismic load due to that nonlinear response. Another thing that's interesting here is this is kind of just an example of why site response analyses are necessary when you have materials that are expected to respond in a nonlinear way. This is the red line shown here is what you would get from just using a simplified analysis using a ground surface peak ground acceleration you can see that there's quite a bit of difference there in the data below about 20 feet. And then this is another summary figure. So this is what I just walked you through is kind of one profile, but we actually have several different reaches. So we have 5 or 6 different reaches. And so even though this is a rather concentrated area, the subsurface stratigraphy does have an impact on our site response. And so we can see here that there's quite a difference here between some materials in the green that are de-amplifying our earthquake ground motions, and then some other locations where near surface are actually quite amplified. So that has an impact as well on our liquefaction potential calculations. And then we can, of course, use our CPTs and our borings to perform our liquefaction triggering analyses. There's a lot of great information out there on how to do this work. This is one example of where we can bring in our results from our 1D site response analyses and rely on that information over the simplified procedure. And we can calculate what are the estimates of estimated settlements and displacements for our pipeline in trying to help support the design and remediation efforts that would be needed. And then lastly, I won't go into detail in this for this presentation, but the data that we did collect was ultimately used to develop and refine a two-dimensional nonlinear dynamic analysis model, where we were able to model the soil structure interaction of the pipeline under these various earthquake loads, and be able to come up with recommendations, recommended displacements and springs for the pipeline designer, so they could design a pipe in configuration that could withstand the anticipated movements during this earthquake event. And then, so in summary, this was a fun project in which we were able to really think through what are the available sources of information that we have, and how can we integrate all of that information into one cohesive kind of interpretation of the subsurface. And that requires, interpretation based on historical data, as well as our current existing, the data that we collect for this project specifically. And all that data, it relates. So we need to understand, how does the shear strength that is estimated from a vane shear test relate to a laboratory triax test and relate to a CPT test. And so all of that information is again used to aggregate and come up with representative parameters for our analysis and design for this project site. And so again, the CPT, the Seismic Cpt is really useful here in this project. And in fact, for this site, we were able to push our CPTs down to 200 feet or so with shear area velocity readings every 5 feet. And so it gave us a lot of good data for performing our seismic evaluations for this project. And that's all I have.
Okay, thanks, Chris. Greatly appreciate that. I think if you look at our sort of sub motto for today's webinar, processing and analysis, making the most of your methods, that presentation definitely encompassed making the most of available methods. Excellent work with a big toolbox, including things like the vane shear test and the seismic CPTU. A lot of information there on stratigraphy and acquisition of the representative site parameters and material properties. So greatly appreciate your contribution with us today. So we're going to turn to the Q&A session and panel discussion for our next half hour. Joining us today for that discussion is Bill Owen. He's a licensed geophysicist who manages and conducts engineering geophysical investigations for California DOT, Caltrans. As chief of the Geophysics and Geology branch located in Sacramento, he's responsible for geophysical investigations statewide for highway infrastructure projects. So we're pleased to welcome him today to help us with some of the Q&A and our panel discussion. Before we get to the discussion, though, I'm going to turn over the session briefly to my co-moderator, Ben Rivers, who's going to talk to you a little bit about user groups and opportunities as we move forward with the A-GaME.
Yeah, thanks, Derek. So some of you probably know just in the implementation stages that we sort of set out for the A-GaME, that we wanted to make sure we continued the A-GaME, you know, that this is not just a 2-year thing and it's gone. So, you know, obviously we've got momentum here. There's value. People, you know, just in these presentations today, I think you see the tremendous value that the A-GaME is supporting. So in that same mindset, part of the implementation process that we had in store was to establish user groups. And the thought was to look at specific technologies like geophysics and televiewers, measurement while drilling, CPT, which already has a users group, but we were going to sort of revamp that user group and rethink the user group concept. So the idea here is that for people who have questions, or these groups would be set up for users and users who have questions, who are novice or who are expert, who can talk through troubleshoot problems and continue the advancement of these technologies. And so right now we sort of have in mind to have a user group for geophysics and televiewers, to have one for measurement while drilling, and to have one for CPT, working with industry, so DFI and the Geo Institute, Aegis, and PDCA and other industry organizations, I think also have an interest in supporting these groups. So from you know, being able to provide support from websites or a platform like this and Zoom, where we could actually share and continue to share our experiences in these technologies. The idea is that the user groups would continue this on. So we're in the process right now of organizing those groups. So I want to put that in your mind and hope that you will contribute to those groups. Let us know your interest in being part of those groups, and we can get you on the list as we sort of get these things up and running and find the leaderships to start these user groups out. So that's all I wanted to share on that. Any questions, feel free to shoot me an email or Derrick, and we'd be happy to explain more. And Derrick, you're on mute, but do you want to, tell me where you want to go from here. Do you want to start the discussion, or do you had some thoughts in mind?
I think now is an excellent time to start the discussion, and we'll include some of the questions that came in through both the chat and the Q&A as part of that. I think an excellent place to start is one that asked about, is CPT recommended in semi-arid soils, southwestern region of the US, weakly cemented soils, collapsible soils, just unusual and specialty soils, right? Maybe we have micaceous sands or loess materials. Would anybody who's on the panel like to talk to using some of these A-GaME techniques in specialty areas and what some of the challenges or advantages might be? Don't all jump at once. And you can feel free to turn your cameras on too.
All right, Derrick, this is Bill. I think I can provide at least one input. We use CPT extensively in California in both Bajada soils, alluvial fans, challenging environments, and it's used all over. It provides very adequate results. The only difficulty we have is, of course, when you're dealing with alluvial soils, you run into problems of early refusal. But that's basically the extent of it for us. And then basically you overcome that by moving over and trying to find another spot. The nice thing about CPT is that it's very fast and pretty inexpensive to run. So if you have somebody out there for a day, you can punch in a lot of holes. So it works out pretty well.
Yeah, and I would just add that anytime you can try to support your CPTs with other data sources as well. So that would help if there's uncertainty with regard to your confidence in using the CPT in a certain location. Get a couple of paired data locations with either SPT or sonic boring or other types of characterization methods to support the interpretation.
Okay. Yeah, I think those are some excellent thoughts. There's also a lot of current and ongoing research work with using the cone penetrometer for specialty and localized calibrations. A lot of work with respect to fissured clays, cemented sands, peat, and some unusual geomaterials. And I think that with geophysical work, being able to determine just the differences in the parameters wherever you have contrasts, combining that with ground truth from the cone penetrometer, just being able to use some of these tools for stratigraphy and extent. But then, yeah, definitely like the CPT soil sampler or traditional borings and being able to run laboratory tests, particularly if you have materials that are unusual. An SPT sampler or a vein shear is probably not going to do miraculously better if you have coal seams or urban fill than the cone. If you have mystery material, it probably requires a lot of poking by different methods to try and figure out what it is. Ben, you get to choose the next question for the team.
All right. Well, there were actually two excellent sort of broad questions that came up that caught my eye. And one of them was in regard to digs in the AGS system. And I know Roger Chandler is also, or he was, I don't know if he was one of the participants that dropped off recently, but if he is still on board, he can certainly correct me if I go astray here. But the question had to do, and let me try to find it, had to do with the fact that there is an existing system in the UK called the AGS that digs is very similar. It is a schema, a data schema. And the question was here it is, was to the life of me, I've never understood the necessity of developing digs, the digs format in the US when AGS had a mature digital data transfer format already that's been used since the 80s, and AGS can also be developed from Gantt files. And my recollection is that AGS was actually one of the groups involved in the digs initiative back in early 2000s. So it's not a either or scenario here. These are standard mechanisms, but I think where the interest was for AGS and for others was the expandability of digs, and the XML GML format provided that. And then the structure later on after in version 2 allowed for sort of a cascading type structure that allowed easy expansion. So my understanding was that AGS was interested in adopting digs at one point, but in any case, if you have a standard and you have a schema and you're using it, that's a good thing. And if you have another one, that's okay, but they're standard methods, and that they can easily be, you can have some type of converter between the two. So the good news is that we have these standards, and I think in the US, with the adoption of the AASHTO standard, PP 102, standard of practice for digital exchange. That sort of sets the standard in the US for digital exchange of geotechnical data. And sort of something that's not quite obvious is that all of those standards, or that actually attaches the dig standards to the AASHTO and ASTM standards. So sort of the data governance is actually handled by the existing standards. So that's sort of how that's going to operate. So just wanted to address that I understand that there are a number of different systems, but there is a reason for why DIGS was developed. And then the other question that came up that I thought was great was had to do with data quality. And let me see if I can find, yeah. So this is from Mike Lewis, and his comment was maybe this has been discussed in the past, but 3 important points I believe we need to keep in mind with respect to subsurface characterization and inquired data are field oversight by qualified geotechnical engineers and geologists. 2, an understanding of site regional geology. And 3, data quality. Without these, I'm concerned that what we have in our database or any database will not be representative. So is there a way to provide some sort of data quality index? So if anybody has some thoughts on that, certainly welcome those. I totally agree that we can't lose sight of those aspects. And I certainly have thoughts, but I will keep those to myself and let other people contribute.
And I guess I'll jump in on that a little. I left a lot of that out of my presentation. I was, because I really wanted to lead into what we're doing with Peng, and that's a very small aspect of what we're doing in terms of data management and data quality. But the data quality standpoint, like I said, you go to these conferences and webinars and TRB, and you see all this futuristic research, but the data quality still is really where it's all at. And I can say, just coming from a state DOT perspective, with consulting experience as well, that sometimes there's just a lot of organizational inertia that you have to get by to get past something that seems as simple as data quality, but just who's in charge of what and who's been doing what for the last 10 years and things like that, I think are really important for us to kind of to handle. I think we each have our own struggles with that at each state DOT for sure. And then part of that discussion, I think there's probably some differences between site variability due to just, the way Mother Nature laid things down, and variability in terms of the quality of the testing and the sampling. And I know there's a lot of really, really good discussion on that in GEC 5. And like, you start reading about it and then it just keeps going on, and you realize this is a huge deal. And I think anyone that hasn't read through the variability discussions in GEC 5, to me, that's the first place to start. And I'm definitely not an expert on any of that, but that's really eye-opening. And as when I have new engineers come in and start training them, GEC 5 is really where I point them, and I tell them to pay a lot of attention to all the stuff about data quality, site variability, the quantity of samples that you get, and all that. So I'll let you guys take it from here.
Yeah, I totally agree. And yeah, GEC 5 I think is a great resource to understand that. And when there are a couple of chapters, in fact, it may be in the lab chapter, where it does talk extensively on the quality of samples and measure and the implications there. So no doubt that it is a big part of maintaining. We need to keep our eyes on that, and also the other aspects of just managing quality. And Ohio DOT has done a tremendous job on even with the dig system and providing files to the DOT. There is a process that they have on checking and making sure that when that data is put into their database, that it is checked, and that's separate from the digs schema and anything, even the PP 102 standard. It does not address quality, but it is something that has to be done. I did have a question for Mike Rogers, and sort of switching gears, going back to MWD here. What Mike presented today covered applying measurement while drilling to drilled shaft production shafts and being able to verify capacities using measurement while drilling during that process. I'm interested in knowing what Florida is doing right now, what steps you guys are taking to take that and take what you get in the field during subsurface investigation and matching or comparing or being able to compare measurement while drilling and applying that into design.
I think really what we're looking for right now is the right opportunity to take that on. I bug Dr. Rhoda about it all the time. We need to address this upscaling issue, going from a 2 or 4 inch core sample to a 4 to 6 foot shaft. There's got to be some variability there that we're not catching. So we want to figure that out as well. So the biggest challenge for us with the MWD and taking that on right now is building out these systems where we can go ahead and put this on any drill rig. So we can have contractors going out there and collecting the data where it's not us doing it internally, because that's very difficult if we're doing this for a full scale project. So that's really what's holding us back, I think, right now, is having that full commercialization of these drill rig systems that would allow us to do that. But we're working on overcoming that, that. So hopefully here in the near future, we'll have a project where we can go out and do small scale MWD and compare it to, the full blown board piles and things like that. And I think we'll have some opportunities coming up here in the near future to do that.
Excellent. Good deal. Thanks.
Yep.
There were a couple other questions that were in there. Any that caught your eye, Derrick?
I think there was one that was related to use of the vision cone. Do any of our panelists have anything they might want to contribute, either about video cone, soil moisture resistivity, or some of the other specialty probes? I will comment that there are a lot of tools out there, and that the more information that we have available, can be used for, a lot of different research work, in the sense that there are projects that exist right now that are looking at various ways to do soil gradation related to particle size analysis, as well as aspects of trying to use different techniques to see if you can measure angularity of particles through photogrammetry and other types of things. So I think that we're certainly accumulating more and more data, so one can expect that new and interesting tools might be developed, and that they could be applied to things like the video cone to help with say particle size and working that perhaps even into some of what we do for scour analysis. So I think there are some exciting things that can be maybe just on the forefront.
And I do have yeah.
Oh, I was just going to say, circling back very quickly to the issue of data quality, it's certainly important. And I think that we are looking to try and capture a lot of metadata in terms of you know, the quality of the spatial quality of through GPS of where we take our investigations, and then also the types of information. You know, you can imagine that when we had, you know, more crude tools, it was okay to say, well, the boring is 20 feet left of the tree, and here's some approximate things, and we're going to write down some sounding values maybe of how often we hit it with a 20-pound donut hammer, and you know, that's going to be how we design the piles. Whereas today, as we get more and more complicated information, now we're trying to figure out, well, did we get the undrained shear strength from direct shear, direct simple shear, triaxial, was it drained or undrained? What sort of other, you know, newfangled tests can we have? Triaxial extension. So, you know, there are a lot of things that we try and record and put, you know, some sort of value on as for kind of what level of effort and reliability the data has. So certainly, as we're trying to get, you know, better data sets together to do all of our research work, certainly some sort of tags on how good the information is, you know, are certainly necessary. And I did want to circle back. One of our viewers, John Benoit, had talked about how he was on the initial group with DIGS, met regularly with AGS, and built the additional or the initial data dictionary about 20 years ago. And one of the things that DIGS was hoping to do, where, you know, it's taken a lot longer than people, you know, thought it would, but because it uses XML and GML, you know, the idea is that web tools like Jesse and Jin had talked about, you know, it's now a native language like HTML. So people will be able to code that in. And I think it will allow, you know, for very easy information transport in and out. Whereas I believe AGS was just basically correspondence files and, you know, the naming conventions. Okay. So I think it's taken it to the next step of an interchange process. Ben, you were going to go with the next question?
Yeah, I was. Actually, I wanted to ask Bill Owen. You know, we didn't really cover a lot of, you know, how geophysics gets put into the design aspects, or what considerations go into design using information and data that's collected, you know, from the geophysics, surface geophysics, or even if, you know, Bill wanted to talk about how, you know, velocity data from cones is applied as well. But just wanted to, for the people who are out there and interested in seeing how geophysics can be applied to design, Bill, can you talk to how Caltrans has integrated that?
Yeah, certainly. I can talk very briefly about it. Within Caltrans, we actually prescribe use of geophysics in our geotechnical manual, both for evaluation of subsurface variability and also to provide estimation of in situ material properties. So essentially, it's applications both for project design and in project construction. You know, for example, project design. We're essentially trying to use geophysics, again, by assessing variability, trying to focus the drilling program and trying to get all of our drilling and sampling focused on areas where we have more anomalies, and then providing estimates of in situ material properties, both in terms of seismic design, coming up with shear wave velocities for development of VS30 and for developing seismic design of the structures. And then also trying to provide a constructability assessment. For example, for seismic, we use seismic a lot for assessing excavation potential and for earthwork factors. So that really is assigned to more for constructability, but it's also used as part of the design as well. So the whole point is that we're trying to get a better idea of defining project risk, and then essentially by reducing that uncertainty early on, trying to come up with a less conservative design and also come up with some better cost estimating. So I don't know how much time we have, but I have a little example. If we wanted to just throw it up, I got basically 3 slides I can put up here. So if Sounds I can, good. Yeah, let me go with a share screen. Let me go in here. So let's see. Let me expand this puppy and go back into the slideshow here. And this was, this one was, let's see, let's go from current slide. This looks familiar to you guys. It's because this was presented at Portland in 2018. This was an example of a project we were working on where we had some major cost overruns on it. We had done some seismic evaluations for excavation potential, and you can see where the original alignment was in green, and right up where this rectangle is, there is a boulder field. And so when we provided the original estimates of rippability for further down the slope, unbeknownst to us at the time, they changed the design alignment and put it up right in the vicinity of that boulder field. Ended up being in right in the middle of some metamorphosed pillow basalts, which turned out to be some of the hardest rocks we had in the state. They had 18,000-pound rams out there, and they were mushrooming the heads on these boulders, especially one of these little boulders right on the top. They were just mushrooming the heads on them, and that ended up being they ended up having to go to blasting for excavation out there, and that ended up being a $2 million cost overrun. So there were other segments of this project that they were very concerned that they were going to have additional problems on. So they asked us to do some additional analysis of the data. And so what we ended up starting to do, we started doing tomographic analysis of the data and comparing it to the original GRM analyses. And doing that, we essentially assigned risk factors to various segments on the project. This is an example of the tomographic results compared to the GRM results. And some of the results were very comparable to the GRM. Some of the results of tomographic analysis showed a completely different picture than what we would have seen in the original GRM analysis. And so we essentially used that to come up with a risk matrix for areas, and basically identifying where we were going to see areas of high probability of coming into contact with unrippable materials during excavation. And what I found out from the project designer, this was basically last week during a phone conversation with them, they were very, very happy with those modified results, because they felt that they ended up with much better project bids for the next phases of the construction. And they felt like they came out, they didn't have any unanticipated conditions out there. And so they felt like they had a very good result from the reanalysis of the data. So that's kind of one of the examples of how we can apply these kind of techniques, both in terms of design and in terms of construction.
Very good. Very good. Thanks for sharing that, man. Very good. So I think, yeah, we're right on time here. So Derrick, was there any final thoughts you wanted to share before we close out? And you are on mute.
Yep. That button. Thanks, Ben. Okay, final thoughts here for webinar number 9. Thank you all for attending this afternoon. We greatly appreciate your participation and the questions that you posed to our team today. Thanks to all of our presenters. It was a really great session. Appreciate you being here and your contributions. February 9th, 1 week from today, the A-GaME Winter Webinar Season Finale for Webinar 10, reporting and visualizing the big picture for a winning A-GaME season. It's another 2-hour special session. We've got a case history about the value of big data, more discussions on data interchange and the benefits of digs, data visualization using augmented reality, a look ahead to EDC 6 with federal highways and digital as-built drawings, as well as some deep thoughts on the added value in the geotechnical field, as well as what's next for the A-GaME. Ben and I are going to be tag teaming the moderation like we did today, and our speakers are going to be Vanessa Bateman with the Corps of Engineers, David Unkefer with the Federal Highway Resource Center, Stephen Taliaferro, Ohio DOT, Scott Anderson at BGC Engineering, and Alan Marr with Geocomp. A really great lineup, and we'll hope that you'll be able to join us next week for our season finale. With that, thanks again to our presenters and our attendees.